Hi everybody. We might make a start. So welcome to Monday Lunch Live and the Victorian Comprehensive Cancer Centre. I'm Grant MacArthur, the Executive Director of the VCCC, and it's a very special Monday Lunch Live today because we've got a very, very hot topic that is borne out by the number of people that are attending. So it's my pleasure to introduce Dr. Dish Herath, and Dish is a very special member of the VCCC community, as he's interestingly dually trained as a nuclear medicine physician, also a medical oncologist. He works across two of our VCCC sites, being the Western and the Peter Mac, and he's also the Joint Chief Medical Information Officer at the Peter Mac. So Dish is ably qualified for today's topic, and you know, today's topic is a pretty damn interesting topic to me. I was just at a dinner meeting last week where we were discussing, is the future of a cancer clinician gone? That clinicians will be replaced by decision-making tools based on artificial intelligence and computers, and surgeons will be replaced by robots, and that we will no longer need cancer clinicians. This was a serious conversation. I mean, that's very science fiction-ish. There were very different views around the table about the future of the clinician, but you know, that's all a bit of sci-fi, and I'll probably be long in the grave before we're really thinking about that. But what I think is really very, very interesting about AI and cancer diagnosis and therapy is the ability of using technology to standardize the delivery of care for patients, so no matter where they enter the healthcare system, they're going to get the likes of the mind of Dish looking after them using information technology. It's very exciting. Everyone's talking about this worldwide as being disruptive in the whole way cancer care is delivered to patients and other areas of care. So really looking forward, Dish, to your thoughts on this very stimulating space. Thank you. Thanks, Grant. And can everyone hear me clearly? Yep. Thanks, Grant. And I'd like to thank Grant for inviting me to talk about this topic. So I think the initial one I suggested was a little bit more pedestrian, but he thought the ones I suggested this would be the most interesting one, so that's what we've gone for. Sorry, just looking at that. Yeah, here we go. Okay, so this is a summary of my talk. So I'll talk a little bit about artificial intelligence in general terms and talk about the difference between general AI and narrow AI, and the basics of neural networks. So I apologise, I'm sure there'll be people in the audience who actually know quite a bit about neural networks, and this will be a very dumbed down version for them. So bear with me, because then I'll get on to, after I've spoken a bit about some non-medical examples of AI, which I think will be of interest to people who aren't familiar with the field, I'll then move on to talk about the oncology stuff, which will be, I guess, the meat of the talk, and talk about some imaging stuff, a system called DeepMind and IBM Watson. So I've got no relevant disclosures or conflicts of interest for this particular talk. Now, in terms of limitations from this talk, I'm a clinician, so that means I don't understand the mathematics of neural networks. I can't program even a simple neural network, and I've got no understanding of translational bioinformatics. So, you know, you might say, well, that's pretty dumb, and I'm sorry, I was coming to this talk expecting that you were going to give me the Python code to cure cancer. So that's not going to happen, and so those are the caveats in advance. So why would you care about what I have to say? Well, actually, I've asked myself the same question, but I think, in fact, it's so what I have done in the past is actually implement software solutions in clinical settings. I've done change management, and I was the clinical lead for the VCCC's Alliance's evaluation of IBM Watson for oncology. So to start off with, what do we mean when we talk about artificial intelligence? So artificial general intelligence is kind of, you know, one type of AI, and this is strong AI is its other term, And while there's different definitions, I think the Wikipedia definition is actually pretty good in this case. So it's the intelligence of a machine that could successfully perform any intellectual task a human being can. And another way of thinking about this is that it's the ability of a machine to learn in one domain and then transfer that learning to different domains. And that's the AI in movies like this one. I think this one's called Ex Machina or something like that. I haven't seen it. And this does not exist. Okay, so it definitely does not exist at the moment. If there's any AI researchers who want to tell me differently, go nuts, but that's my opinion that it exists. On the other hand, narrow AI, which is, I think, inappropriately called weak AI, because it's still capable of doing some pretty amazing things, is designed to perform a specific task. So this would be things like facial recognition, for instance, what Siri does, which is a number of things, but includes speech recognition. Self-driving cars, you could argue, are a number of different AI systems, but it's still in the realm of narrow AI. And so there's multiple real-world applications, and this is going to be the focus of my presentation. Now, there are downsides of artificial intelligence, and they are real downsides. So people worry about artificial general intelligence wiping out humanity. I'm a big fan of the original Terminator movie, and Skynet in Terminator is an example of this. And sometimes when people see new AI systems, they want to call them Skynet as well. But I think this is actually unlikely to happen in the near future. But I think people should be aware that narrow AI is absolutely capable of being developed in a way that it can kill people. And an example would be autonomous weaponized drones that are trained to recognize specific targets and then eliminate them. And that kind of research I'm absolutely sure is going on. And there's some very smart people who are concerned about this, including Elon Musk, Bill Gates and Stephen Hawking, and have spoken up about it. Having said that, I'm not going to talk any more about that downside of it, and I'll leave it for those luminaries to sort out, because I'm going to try and focus more on the medical uses and medical applications. So what's AI up against? It's up against us, okay? And a single human brain is a pretty tough competitor. So 86 billion neurons and roughly 21 billion in the cerebral cortex, with most of the rest in the cerebellum. That means you could actually argue we use far more brain power from stopping ourselves from falling over when we're drunk than we do actually thinking about things. But, be that as it may, we're a pretty good machine ourselves. So there's about 7,000 synapses or connections per neuron, which gives a total of 150 trillion synapses in the brain. So, very, very complicated and impressive organ. This is an oversimplified version of a human neuron, and basically you've got impulses that are coming in through the dendrites being processed. Sorry, just trying to find, whoops, trying to find my, where's my thing gone? There it is. So impulses coming in through the dendrites, being processed by the cell body, and then there's an output from the axon. Now, it's a little bit more complicated than just an on-off thing. And, as more neuroscience research is being done, it's quite complicated. But you get the idea of the model here. And that's really the model that artificial neurons, that are the basis of artificial intelligence, are based off. And with an artificial neuron, what you've got is numerical inputs coming in on one side. They're processed at a node, and there's a mathematical function performed by the node. And this can be something like a sigmoid function that will squish the numbers between -1 and 1, or rectified linear unit, which will basically squish it. Basically, if it's less than 0 or 0, it'll go to 0, and above 0, the number is preserved. But you get the general idea that there's a mathematical operation and then an output. So when we combine lots of these neurons together, you get a neural network. And so this is an example of that. This is what's called a feed-forward neural network, or a multi-layer perceptron. And you've got a number of input nodes on this side going through, and then at the other end you've got the outputs, and in between you've got lots and lots of these neurons and what's called hidden nodes. And so when there's multiple layers of this can be called a multi-layer perceptron. An example of how this might be used in cancer is, say you were developing a neural network where you were trying to work out whether, based on the histological features of a breast cancer, it was benign or malignant. So those are your output classes. your input classes are then various histological features, and it's trying to work out which of those is important or which of those is more important. So none of this is going to work without machine learning. So machine learning is the foundation of the success of narrow artificial intelligence, and it requires a training data set with known inputs and outputs, generally speaking. Now, deep learning, which you may have heard of, is a type of machine learning, and there's multiple processing layers and multiple layers of abstraction, and that's what separates it from just straightforward machine learning. So I'd like to give an example of machine learning, and I again apologise to anyone who knows a lot about this for how oversimplified it is, but I'll just talk a bit about backpropagation and how that works as a learning technique. So let's say you've got a input of a cat, and you're trying to get the neural network to learn to recognise the cat. All right? So you might feed in different features of the cat, like ears, cute nose, whiskers, that kind of thing. And a human looking at this image will almost all humans will immediately recognise this as a cat, and so we know that the probability that we're trying to get for the output is 1 for the cat and 0 for a dog, if that's your other output class. Now, an untrained network might, as its initial guess, have a 50-50 guess as to what this is. So it might say, well, I'm not sure if it's a cat or a dog. So as part of the training process, there's an error calculation that occurs. So for the cat class, we know that the true probability is 1, and the initial probability guessed by the network's 0.5, so we've got an error measurement. And what is then done is, remember, these connections are numerical values, so there's an adjustment made to these connections based on that error value. And then when all the connections in that rightmost layer are adjusted, then the backpropagation step is that the changes in the network weights are adjusted going backwards back to the input class. And obviously this is an oversimplification. In a real neural network, there may be thousands of nodes, and so the actual mathematics around this and the calculations are quite complicated. But it can certainly be done. So once the network's been trained, you can then use it to determine outputs from inputs that it hasn't previously seen. And so that's the basis of getting it to actually work. So I'd like to move on and talk about some success stories of narrow artificial intelligence in the non-medical field, which I think will be of interest to people who haven't seen these before. And the first one's a system called AlphaGo, which some of you may have heard of. So Go is a board game that I understand was invented about 2,500 years ago in China, and this is far more complicated than chess. There's actually more board positions, so there's more places, so white and black stones that you place on the intersecting lines of the board, and it's so complicated there's actually more potential board positions than there are atoms in the known universe, which means you just can't brute force solve this, you know, with a straightforward computer. Now here's an article from 2014, way back in 2014, just shows you how fast things move in this field. And this is from Wired magazine, and it's basically comparing the performance of a computer system with a Go Grandmaster. Right? Now I'll let you see if you can guess which one's the computer guy and which one's the Go Grandmaster, but I'll give you a clue. The guy with the skivvy and the glasses and the laptop is the computer guy, right? And the guy wearing the robe, I kid you not, his name is Grandmaster Yoda. Okay, it's right there in the thing. Okay, so basically Grandmaster Yoda played this computer program called Crazy Stone, and Yoda won, right? So Wired magazine said, the mystery of Go, the ancient game that computers still can't win. And back in 2014, Wired magazine predicted it'd be about 10 years before a computer could beat any of the top Go players in the world. So what actually happened? In 2016, Google had developed they took over this company called DeepMind. There wasn't, I think, their own internal development. They took over DeepMind, and DeepMind's, you see the word deep gets used a lot. I think this goes back to probably deep thought from the Hitchhiker's Guide to the Galaxy, but that's a different argument. But anyway, Google's DeepMind software beat not just any player, but at the time the guy considered the #1 player in the world, Lee Sedol, a Korean, and the scoreline was 4 games to 1 in favour of the software. And I think I saw on the BBC on Friday night the current top player, who's I believe a Chinese guy, also got beat. So how did AlphaGo win? And it was partially through the use of what are called convolutional neural networks. So an oversimplified view of convolutional neural networks is that they've got layers, and what they're trying to do is compose information together. So in the first layer, for instance, the neural network might learn to recognise edges if it's doing facial recognition work. It'll then put those edges together to recognise features such as eyes, nose, mouth, and it'll then put those features together to be able to recognise faces. So that's how you train it to do facial recognition. Now, this is, to be clear, this is not what the computer sees, okay? This is an abstract representation of it. This is very different to what the machine's actually seeing. So when AlphaGo won, what it did was not use just one neural network, but multiple neural networks, and also a process called Monte Carlo tree search. But for instance, one of these networks, the Supervised Learning Policy Network, that one alone looked at 30 million board positions in games that had been played and saved on a Go server in the cloud. So you get an idea of the sort of the scale of the training that's required. This network, this other one, what it did was it played games against itself. So the computer played games against itself, took snapshots, if you like, of board positions and worked out how to win from there. And that way, it was basically, as I said, beat the top player in the world, and at least 8 years earlier than the Go expert. So the next thing I want to talk about, the second real-world example, is Google Translate. So in 2006, Google launched their Google Translate service, and this uses phrase-based machine translation as its key algorithm. Now, this service is very important worldwide. Living in an English-speaking country, we may not appreciate the importance of this, but for instance, Google Translate web apps do about 18 million Chinese to English translations every day. Now, in 2016, Google changed over to a new process of translation called neural machine translation. And neural machine translation is based on a type of neural network called recurrent neural networks. So here's a view of what a recurrent neural network would look like, taken from this Nature review. And basically the difference here, so you remember with the feed-forward neural network, the inputs went right the way through to the end, and then the learning was done. The recurrent neural network learns as it goes. So basically you've got an input coming in here, it's processed, and an output comes out, but in the processing step, there's also a learning step, which is this circular thing. So the next time an input comes in, the processing has learnt from the previous input. And so it goes, basically. That's why it's called recurrent, because it's this step being repeated. It's a bit more complicated than that. Well, it's a lot more complicated than that, but that's kind of a, clinician's view of it. Now, here's a pictorial representation of how Google Translate would do this. So there's a Chinese sentence on the top level, and what it's doing is the encoder step is converting the characters into vectors. Now, for each vector, what it does is it will take the word that it's in front of it at the moment, plus it'll do a look at the vector that's a summation, or a summation of the previous vectors up till that point from previous words. So it's not just looking at the word in front of it, but the data that's coming up till that point. Now, and then there's this decoder network, and what the decoder network does is it'll pay a variable amount of attention to each of the encoder steps, and on the bottom you can see here, it'll then put out the translation. In this case, knowledge is power. Right? Now, it's a bit, this is a bit oversimplified. In fact, there were multiple layers to both the encoder and the decoder, but you get the general idea. Now, there's large data sets that are available to train these neural networks. So, for instance, the English to French training set contains about 36 million translated sentence pairs, and that's only one of the data sets that's used to translate these systems, that's to train these systems. So how good was this system, the new system? So here's the input sentence, and here's the translation using Google's old phrase-based machine translation. Now, when it says phrase-based, what that means is it's taking chunks of words. They're not necessarily linguistic phrases, they're just sequential groupings of words. And the green is the artificial intelligence system, and here's the human. So if we look at the first line, Li Qiang Premier added this line to start the annual dialogue mechanism. Sounds a bit clunky. The AI system, Li Qiang will start the annual dialogue mechanism. Significantly less clunky and much closer to the human translation. And in fact, when Google looked at their translation quality for multiple language pairs, the AI system was doing significantly better than their old system and getting much closer to human level translation, with 6 being what's considered a perfect translation. Now, while that's actually pretty impressive as is, the next thing is, I think, even more impressive, and this is basically that using the same methodology, Google was able to translate language pairs that had not previously been seen by the system, which I think is just astonishing. So an example of this is, say the neural machine translation, the AI is trained on English to Korean and its matching pair, and English to Japanese. It can then, having never seen Japanese to Korean, because it's seen the linking language, it can do a direct translation of those. Not as well as it would have if it was trained, but not in a bad way at all. And then, so why would it be able to do this? So this is a representation, if you like, of how Google Translate sees language and sees sentences. So the colours here, each colour is ignoring, on the left side of the diagram, each colour is ignoring the language that was the phrase is in, and is just looking at the meaning of phrases. And you can see how most of these colours are clustering together, right? And so if we take an example of this red one and blow it up, that cluster of the same phrases actually contains the same phrase in 3 different languages, English, Korean, and Japanese. That means that the AI has trained itself not just to do translation of word sequences, but it's actually understanding to some extent the semantics of language and the meaning of language. And it's done that really by just being shown lots and lots of language translations. So just to summarise that, using recurrent neural networks, Google significantly improved the capabilities of Translate. And as I've said, now it can translate things that it hasn't seen before. All right, so that's enough about non-medical stuff, because the title of the talk was cancer. So let's move on, and I'll talk about applications of cancer diagnosis and therapy. Before I get into it, I'd just like to put this out there. So here's a quote from a guy who was considered a tech guru and probably still is. So he said, this guy Vinod Khosla said, eventually we won't need the average doctor and we'll have much better and cheaper care for 90 to 99% of our medical needs. We'll still need to leverage the top 10 to 20% of doctors, at least for the next 2 decades, to help bionic software get better at diagnosis. So a world mostly without doctors, or at least average ones, is not only reasonable, but also more likely than not. So that's his opinion, and other people have expressed these concerns. So let me go through it and we'll come back to that at the end. So first of all, I'd like to talk about cancer diagnosis and the use of artificial intelligence for medical imaging. So there's been a number of areas where this has been looked at, and one example is pulmonary nodules. So this is trying to differentiate benign and malignant nodules and to identify nodules. So here's a slice from a CT scan on the left side, and on the right side what's happened is software's come along and tried to pick out the nodules within the CT scan. Now, the main area where it's actually been successful is in mammography. And this is in digital mammography, and it's the field that's called computer-aided diagnosis. And it's worth noting that there's tens of thousands of published papers looking at machine learning in imaging. But despite that research, clinical adoption is really been only in mammography, not in other areas. And here's an example again of a machine trying to pick out breast calcifications on a mammogram. So what are the reasons for the limited adoption of computer-aided diagnosis despite this vast amount of research? Well, the main problem, I think, and this is a problem across artificial intelligence, and it also applies to things like self-driving cars, is the black box problem. And it's really that neural networks cannot explain why they've made the decisions that they've made. You've got to remember, I showed you that diagram showing the multiple layers, the huge number of connections in a neural network, and each of those is associated with numerical values. It means that there's a huge number of there's a huge amount of mathematics that's not easily understandable by a human being. So to give you an example, this is an image showing how a neural network sees pulmonary nodules in these diagrams and breast ultrasound lesions on this side. Now, even for those of you who have never seen medical imaging, I can assure you this is not how any medical imaging person would look at these particular methodologies, and these make no sense to an imaging person. So that means that humans can't actually understand the conclusions or the techniques that the machine's using. It's a black box. So there are some other reasons for limited adoption of computer-aided diagnosis. One is that human radiologists are actually pretty good at their jobs. So for instance, one paper quoted at a 79% sensitivity for breast ultrasound diagnosis, and radiologists will be better than that. There's also a lack of reimbursement in the United States for computer-aided diagnosis apart from for digital mammography, and that's, may well be a factor. The other thing is that it's worth noting that even though this technology is out there, about 62% of radiologists do not actually change their interpretation based on the computer's opinion. And that it's a little bit unclear as to whether this is due to false positives, which is definitely a concern, or whether it's resistance to change, and it's probably both of those things in reality. However, the performance of this software continues to improve, and the machine learning techniques are getting much more sophisticated. In my opinion, the short-term focus of this should be to improve accuracy and efficiency of imaging specialists, not to compete with them. And the reason I say that is that there's evidence already that digital mammography might have better sensitivity but less specificity than radiologists. So they can be, in fact, complementary to each other. But radiologists, understandably, are worried about their future. And in fact, I hear that people who are considering going into radiology are actually emailing specialists and saying, should I consider this field? Am I going to be replaced by a machine? And interestingly, so some of you may have heard of Jeff Hinton, who really is an AI expert and is involved now with Google and is a very serious academic, and he thinks we should stop training radiologists now. With the greatest of respect to Jeff Hinton, I think that indicates that he doesn't actually understand that much about what a radiologist does. And I think radiologists will still be an important profession. They've had to adapt to change all through their careers, and I think they'll be able to adapt to this, assuming that they go with it rather than, try and act against it. And some examples of this would be, if you've got a 1200 slice CT scan from a trauma series, that could certainly use some AI assistance. They'll have more time to engage with clinicians in the multidisciplinary meetings that they're doing now, and people can correct me if I'm wrong, but I don't think a robot's going to replace an interventional radiologist in the near future. Maybe later on, but not straight away. All right. So that's as much as I'm going to say about imaging. I'd like to talk about this other AI system called DeepMind. So DeepMind, it was developed in Mount Sinai in New York, and it looks at aggregated electronic medical record data, and they've had electronic medical records since 2003. So they've got a vast data set to work with, millions and millions of patients, and they selected a subset of about 700,000. And they use this, so they've used this for a number of different things, but one of the things they've looked at is to predict the probability of patients developing various diseases in the future, including cancers. And the neural network that they used was what's called a stacked denoising autoencoder. Now, what's a stacked denoising autoencoder? I hear absolutely none of the clinicians ask, but I'm going to tell you anyway. Or at least, my simplified understanding. So an autoencoder is basically the difference between that and the other neural networks I've talked about is what you're trying to do is reconstruct or replicate the input with the output. So this really reduces the need to annotate and label your training data set because you're trying to get an input that closely resembles the output. And you guys might very appropriately say, okay, you've just described a photocopier. Why do we need artificial intelligence to do photocopying? Well, you don't. But the thing about the way this neural network works is that while the input layer and the output layer should be similar, in the middle of this neural network, there's a bottleneck or a hidden layer. So in other words, when the neural network is looking at stuff, it needs to find a way to throw out the useless information, the noise, and reconstruct the output based on a minimal data set. So it's really focusing on what's the critical information in this data that's coming in. And so here's an example of it removing noise from a series of numbers. So the noise images on top and the clearer images of numbers on the bottom. So what happened at Mount Sinai was that they had their hospital data warehouse and their electronic records. So, lots of information like clinical notes, diagnoses, medications, and they fed this into the neural network and done this unsupervised learning and then produced a number of different feature sets. But one of these feature sets, and the one I'm going to talk about, is this disease prediction, the ability to predict diseases in the future that the patient does not have yet. And if we look at their results in terms of the ROC curve, so this is, I think, true positives plotted against false positives, and we look at the subsets that are the cancer-related ones, so cancer of the rectum, liver, prostate, and myeloma. Now, these other columns, so this is the deep patient results. These other columns are more classical methods of feature extraction, and you can see that deep patient's doing significantly better than the other methods of classifying patients, and what looks like pretty impressive numbers under the ROC curve. And if we actually then look at accuracy, again, we've got the different techniques of classifying features and predicting disease compared to deep patient. And the accuracy is about 93% for deep patient, which sounds very impressive. I mean, you would think that a 93% accuracy of being able to predict disease in the future is really, really good. But there's a little number in the column here, which is hidden away, but is also important. This is the F-score, and that's only 0.18, which is 18%. So what's the F-score? The F-score is a harmonic mean, as I understand it, of the precision, which is equivalent to a positive predictive value, and recall, which is equivalent to sensitivity. And that's a less impressive number at 18%. So what's the actual precision of the system? So if you look at the precision, again, for predicting disease in the future, here's deep patient compared to the historical, not historical, but other methods of predicting diseases. And it does better, but in fact, its precision is about 0.4 or about 40%, which means that of disease predictions it's making, if it predicts a disease, 40% of patients will get that disease, but 60% will not. So it's about 60% false positives. Can we work out what the actual sensitivity of deep patient is? Well, you can kind of do a dodgy calculation to work it out because it's not quoted. And the caveat here is I could be wrong about this because this is my best guess based on the data presented. But I think it's about 12% sensitivity, okay, which doesn't sound so great. So how come there's a high accuracy but a low sensitivity? It's because most of the time your predictions are going to be true negatives, which bulks up the accuracy. An example of that is if I went through 100 people and was trying to guess which one of them is actually a cat disguised as a human, if I predicted only 1 out of 100 people is in fact a cat, and I was wrong, there are no cats, then my accuracy is still 99%. I'm 99% accurate for predicting cats wearing human skin, right? And it's the same thing when you look at these data sets. So in summary, deep patient is absolutely a step forward. It's superior to existing models. And the other thing importantly is it demonstrates the secondary things you can do with an electronic medical record. But it's not ready for clinical use. This is still, in my opinion, in the area of research. I wouldn't be trusting its disease. The final clinical area I'm going to talk about is IBM Watson. So IBM Watson is IBM's platform of technologies that is essentially a narrow AI platform, though it incorporates other things as well. And here's the most famous thing it's done, which is to win on the game show Jeopardy. So Jeopardy is a general knowledge quiz show, which means it's open domain. People can get asked all kinds of general knowledge questions. And these are the world's two top human players up till that point, and Watson's sitting between them and has beaten both of the top human players. And the number one player, this guy Brad Jennings, has actually said underneath his answer, "I for one welcome our new computer overlords." Okay, so that was his opinion on it. So how does Watson develop the capability to be able to win a general knowledge quiz? Well, it's got multiple technologies underlying it. So it does natural language processing to be able to understand language. It generates hypotheses and then tests those hypotheses against evidence, and it will also learn from user feedback. Now, because it's a commercial system, the actual technology underlying as it is a lot more opaque than what you'd get with, you know, the stuff that's been published in research papers for neural networks. So bear with me, because I'm not going to, well, some of you might be really happy that I'm not going to show any more interconnecting lines and things. But, well, I'm going to show some. So here's an example of how Watson works in the quiz show, right? So here's a question. In 1698, this comet discoverer took a ship called Paramore Pink on the first purely scientific sea voyage. Now, I don't even understand that. Lots of people wouldn't understand what the hell that's trying to get at, let alone a machine. So how does a machine figure out the answer to that? Well, it breaks it down into keywords and works out what's a date and how the words match up to each other. And then it'll do a primary search of its data set. And from that data set, it will come up with candidate answers. So, you know, ranging from Isaac Newton to the Pink Panther, okay? It'll then do, and it could be hundreds of answers. It'll then do a secondary search where it's going through its evidence base, looking for evidence to match each of those answers. And then it'll match that evidence against a whole series of different algorithms, including temporal and spatial algorithms. So, for instance, Pink Panther scores pretty poorly on both temporal and spatial. He actually wasn't on the Paramore Pink in 1698. Okay, but on the other hand, Edmund Halley of Halley's Comet fame was in fact in the right place at the right time. And so then when Watson's merged and ranked the scores, it'll produce a confidence value, and it thinks that the most likely answer is Edmund Halley. Pink Panther doesn't even get a look in, and so it'll answer that question, and that's how it won Jeopardy. And so you might say, gee, who cares? That didn't help me at all with cancer. So how did they apply that in the cancer domain? So this is how Watson for Oncology works. So Watson for Oncology was developed by IBM in collaboration with Memorial Sloan Kettering in the US. And the way it works is it gets fed data. So for instance, unstructured data such as flat files where you get with histology or radiology reports. It'll do natural language processing on those to convert that into structured information, or you can directly enter the structured data, or it'll get structured data fields from electronic medical records. And it can also get unstructured data and process it from EMRs. Once that processing is done by Watson, it'll then spit out treatment recommendations. At the time we were testing it, that was primarily chemotherapy treatment recommendations, but subsequently it's developing more capabilities. And I believe by July this year, it'll be able to cover a lot more cancers. So a couple of years ago, we actually received an innovation grant for the VCCC Alliance to do an evaluation of it. And what we learned when we looked at it was that the treatment recommendations, even though you know, you would hope that it's going to look at a very large set of published papers and things for its treatment recommendations, and it did do that. The primary thing it was looking at was Memorial Sloan Kettering patient cases, and I'll come back to that. But the next thing I want to talk about is the natural language processing capabilities, which was what we looked at as part of our evaluation and did a research abstract on that. So as far as natural language processing is concerned, we did an ethics-approved project where we tested the accuracy of NLP for 50 de-identified patients and 264 documents across those patients. And we looked at 32 data elements, including performance status, histology, mutation status, that kind of thing. Here's an example of Watson looking at some flat files and trying to identify concepts, or trying to identify words, really. So in this case, it's identified from the histology report that this patient has adenocarcinoma and that the biopsy done was a fine needle aspirate. So it'll then convert that into structured data for processing. Here are our results. So accuracy of 94% sounds good, but remember I just told you accuracy is a very dodgy number in these situations. So more importantly, the precision or the positive predictive value of 85% and the recall or sensitivity of 89%. And remember, this has not been trained on any VCCC data sets or Australian language or any of those things. So it's not bad. Where it did well was for things like histology, performance status, M stage. It was actually pretty inaccurate for primary tumour size, mainly because there were a lot of other measurements appearing in the records. So, for instance, if there was a measure of the primary tumour, but also a measure of the metastasis, it'd get confused as to which one it should measure. So that was the natural language processing. What about the treatment recommendations? Because that's what Watson is, working on. So we actually decided not to pursue the implementation of Watson for oncology. I think it was Grant's predecessor who made that final decision. And there were a number of reasons. So it wasn't just one reason. There were a number of reasons, funding, but also we were hoping as part of the Connexus project to get a health information exchange, and then beyond that to get an electronic medical record. And you'd really need either or both of those things to be able to implement this in a meaningful way, and we didn't get either of them. And also, but really the other thing that concerned us was this case-based training on Memorial Sloan Kettering cases. Don't get the wrong idea. I think the Memorial guys are really good oncologists, far smarter than I am, far, far smarter and more accomplished. But it means that if you're training on Memorial cases, that's not directly applicable to the Australian setting. And the other concern I have is that case-based training can become outdated. And I'd like to talk about how case-based training can become outdated, again, using the example of cats. So cats do not historically change that much. So this is a picture of a cat sitting in the cannon. It's not getting shot out of the cannon, it's actually having a rest on the HMAS Encounter in 1918, all right? And this is a much more modern picture of a cat that couldn't find a cannon, so it's just decided to wrap itself up in paper. But you could train a convolutional neural network on images from 1918 right up till the modern day, and the neural network will be able to recognise that they're all cats because they look like cats. On the other hand, that's not the case for cancer treatment. Cancer treatments change, and they change fast. So here's an example of the Keynote 24 study, which was published last year. And this was a comparison between pembrolizumab immunotherapy and chemotherapy for stage 4 lung cancer patients. And what this showed was pembrolizumab was superior to chemotherapy for about 1/4 of stage 4 lung cancer patients. Now that's fantastic news for patients, assuming we can get access to the drug for them, which is another conversation. But the significance for a neural network is that training data set you use is now completely obsolete, and you need to retrain if you're going to use that as your source of truth. Now, it's worth noting that there have been advances in Watson since we've looked at it, and other people have moved forward with it. So this is a group of hospitals in India, but it's not just in India. I believe there's a hospital in Palm Beach which implemented Watson earlier this year as well, Palm Beach in the US. But this Indian group of hospitals, you can actually upload, or I don't know if we can, but certainly Indian patients can upload their documents to Watson, and it'll give you a treatment recommendation. And you get to pay for it, of course. All right, so people are moving ahead with that, but it hasn't been all smooth sailing. So some of you may be aware of this. So this headline is IBM's Watson proves useful at fighting cancer except in Texas, which refers to the fact that the MD Anderson had a completely separate implementation of Watson from Memorial Sloan Kettering, and theirs crashed and burned. But you could actually argue that that had nothing really to do with the software itself. It was more to do with a combination of factors, including a dodgy financier who promised a donation in inverted commas of $50 million that never turned up. Some fairly dodgy practices around how they accounted for risk and what was research and what was clinical. Google it, it's an interesting story. I'm not going to cover it further, but I don't think this negates the promise of the underlying technology platform. So my summary about that is the VCCC did not implement Watson for oncology, but we certainly would like to do further work with IBM. It's worth noting that one of my colleagues, Peter Gibbs, who's a colorectal oncologist, is collaborating at the moment with the IBM Research Lab in Melbourne on a colorectal cancer project. And we are also discussing with IBM looking at testing Watson for clinical trials matching purposes. So with regard to narrow AI, the sort of summary of this is that rapid progress is occurring. Non-medical fields have seen AI implementations with Google Translate probably being the most impressive. But while there are some exceptions, narrow AI in oncology is still in the realm of research and not in clinical use. So what are the barriers? So I've discussed some of these already, but just to go through them again. In imaging, you can look at mammography and the machines will do a good job at that. A CT scan is a far more complicated thing than a mammogram, and it's very hard to get a labelled annotated data set to train from. Even for a convolutional neural network, it's not easy to look at a CT scan. As far as both imaging and therapy is concerned, as I've said, up till now, large annotated data sets are required for training and as the source of truth. That may actually change in the future. Machines may get better at actually learning how to label data sets for themselves. But the current requirement for annotated data sets, these do not exist in medicine at the scale required to train a neural network, which is, in my opinion, in the hundreds of millions of cases. And as far as therapy is concerned, source of truth for therapy, so what you're even going to train the neural network on is a moving target as new therapies emerge. Now, I don't think any of these are permanent roadblocks. They are challenges. I think, as I've shown you, what happens with AI research is that challenges get overcome. So progress in AI is rapid and can be unexpected. And I think, we've seen that with the non-medical examples. So the question is, if there is an improvement, what will oncologists and other cancer clinicians do if narrow AI improves to the point of doing some tasks better than doctors? And the answer is we'll adapt, in fact. So just to segue a little bit, the VCCC does a patient experience survey, and the results were recently released, though they're probably confidential and I shouldn't speak about them, but what the hell, I'm going to anyway. So, at the risk of blowing our own trumpet, I think you could say that as a group of VCCC hospitals, we're actually doing a really good job of providing patient care. I'm sure some people would disagree with that, but I think if you look at the statistics from the surveys, we're pretty good, but there's definitely areas for improvement and multiple areas for improvement. So for instance, in areas like number of patients asked to participate in cancer research, where the patient's views were taken into account when discussing treatment options and where the side effects were explained in a way that patients could understand. So I mean, there's a lot of work that I could be doing if I get an AI buddy to help me out with some of my current work at the moment. So I'd love to have an AI system. So just coming back finally to this quote from the tech guru Vinod Khosla, that doctors are going to be replaced and that we'll only need a few of them to train the super systems, and that pretty soon we'll all be out of work. So my response to that is, in fact, this, which is computer says no at the moment. All right. So I'd just like to acknowledge a few people. So Karen, who's in the audience, is a professor at University of Melbourne and sent me a really good review article and was able to discuss a couple of ideas on the talk. So any errors in the talk are entirely on me. Karen didn't actually vet the talk. Other people I'd like to thank are my collaborators on the Watson evaluation, and so the Parkville EMR team. Thanks for the guys in the audience and the rest of the team. So some of you may be aware we didn't get funding in the state budget this year, but we're absolutely not giving up on the idea of a Parkville EMR. I think I've shown you some of the secondary uses of it, but the real reason we're still pushing for it is the patient safety and quality and efficiency benefits of that. So we're far from giving up on that. And thank you.